Hi, everybody. This is 4N, potential energies of systems here. So the scenario is we got an astronaut is lost in space near an alien planet and its orbiting moon, shown at the right, not to scale. At a particular instant, the moon is directly opposite the astronaut on the far side of the planet, in line with the center of the planet, and at a distance r from the astronaut. So first question here, mark an X on the diagram shown to indicate the location where the astronaut could move so that she would feel no net gravitational force. So besides infinity far away, she'd have to be equally pulled one way by the planet and the other way by the moon. So we got to be in between. And the other thing then to consider is since the moon is smaller, we have to be closer to it than the planet for it to pull with an equal force there. So next part here, it says that if the planet were not between the astronaut and the moon, but the distance r was the same, would the gravitational force on the astronaut by the moon, that's important, on the astronaut by the moon, increase, decrease, or remain the same? So imagine we could suddenly snap our fingers and this planet was gone. How would that affect the force of gravity on the moon, or from the moon on the person? And it wouldn't at all. It would stay exactly the same because that force of gravity is going to be equal to big G times the mass of the astronaut times the mass of the moon divided by the distance between them squared. And that's true whether or not the planet is there. The planet would add an additional force, but that force stays the same whether or not the planet is there. Okay, so next part here, it says, the astronaut's jetpack is powered by an arc reactor that can supply nearly limitless energy to the suit's thruster. The astronaut wishes to escape this planet-moon system and travel to other parts of the solar system away from any significant gravitational effects of other planets or moons. Consider the energy required to escape the configuration shown above. If the astronaut were instead standing on the moon, would this require more or less or the same energy to escape from the system? So in other words, they're saying, consider this situation right here and the energy to escape this situation, and then what if instead they were standing like right here instead? Here, we got to complete the drawing. There they are. They're standing there. So would this situation take more or less or the same energy as this situation over here? Well, to think about it, let's think about we have some gravitational potential energy. We are in the well, so to speak. So this is where we will use our gravitational potential energy sort of space equation here. So this is the well that we are in. We can see here that our gravitational potential energy is inversely proportional to radius. So in other words, as r gets smaller, this energy required to escape gets bigger. So we will require more and more energy. The smaller r is, the bigger this is. Think about it kind of like this. Imagine we're in a well, and you can climb so far down the well to start. The further down the well you climb to start, the more energy it's going to take to get back out of that well. So as you get closer and closer to the moon, you're getting further and further inside its gravitational well. All right, next part here, part D. It says, the astronaut is able to fly a very far distance, X away from the planet-moon system at a constant velocity, needing a total amount of energy E to do so. Explain why the jetpack must do work on the astronaut to maintain a constant velocity. Well, here's the thing. No matter how far we get from that planet until we get infinity away, there will always be some force of gravity from that planet-moon system on the person. That force of gravity is doing negative work. Why? Well, let's say the astronaut's moving off to the right. That force of gravity is always pulling them back the other way there. So if we want to keep a constant velocity, which means a constant kinetic energy, then to make up for this negative work, we need positive work done by the jetpack there. Otherwise, we'll lose energy due to the negative work of the planet-moon system. Okay, so that's part I. Part I of D says sketch, that means we just want the basic shape, sketch a graph of the force exerted on by the jetpack versus X to keep the astronaut at a constant velocity again. And by the way, this is the force exerted by the jetpack as she moves away from the planet-moon system. Identify the feature of the graph that could be used to determine, so the feature of the graph that could be used to determine the energy used by the jetpack. One thing that I think confuses people and they think it's more complicated than it has to be, is they say the force exerted by the jetpack. But the force exerted by the jetpack to keep us moving at a constant velocity has to be equal to the force of gravity exerted by the two planets. Now let's just sort of assume them as one thing, one distance away. We look at this equation right here. So the force of gravity between the astronaut and the moon planet system is proportional to 1 over r squared. So that's the key thing here, right? Force of gravity is proportional to 1 over r squared. So we want a 1 over r squared shape here on our graph. Now you just have to sketch it. A 1 over r squared is basically like that. But just to emphasize that point, I'm going to do it a bit like this. So 1, 2, 3, 4. I'm going to say I have a dot right there, 4 up at x. If I'm 2x away, if I follow this, 2x away gets squared, that will be 1/4 the force. So it should only be 1 dot up if this was 4 dots up. And then the basic shape is like this. And then it goes on out for infinity there. So another part of this question that we can't forget is they say what feature of the graph could be used to determine the energy by the jetpack. So when we look at this one here, what we're talking about is that the energy needed by the jetpack is equal to the work the jetpack has to do, which is equal to the force times the distance. In other words, the area. So this area right in here, and you would need calculus to actually find that area since it's a curve, but that would tell you how much work is needed, how much energy is needed by the jetpack to get us through there. All right, one last one here, and it says, describe the power required from the jetpack as the astronaut travels away from the planet-moon system. So do we need more power as the distance increases, same power regardless of the distance, or less power as the distance increases? I think almost everyone will intuitively think that one, and they are correct there. So why? Well, remember, the work done by the jetpack, which is related to the power, right? Because power, actually, let me write up here, is the work per time. So we're basically asking about the work needed here. Work is force times the distance we move it, but that force, again, is related to the inverse of r squared. So as we get further away, as r gets bigger, then F gets smaller, which means we have to do less work, which means we need less power.